Hey, here we go. Short and sweet today. Did you know there's water in the atmosphere? Like there's water above your head. Not just in a lake, not just in a pond, a river, stream. There's water up, not just down. Here we go. There is water all the way. Water may not be the most abundant gas in the atmosphere, but it's the most important in terms of our weather and in terms of understanding atmospheric processes. Water vapor is absolutely the most important to figure out what's going on with it. All right. Solids, liquids, and gases. On Earth, those occur very naturally. Water occurs in all three phases at pressures and temperatures available on Earth. Okay? We are used to solids, liquids, and gases. We are used to melting and vaporization. We are used to condensation and freezing, moving back and forth between solid to liquid, liquid to gas, going warming, melting, warming by vaporizing, cooling by condensing, and cooling by freezing. We're going to add two more. We're going to add sublimation and deposition. The common example, the only example, the one you're going to be the most familiar with, if you're familiar with any at all, is dry ice. Carbon dioxide at normal atmospheric pressure skips liquid phase. You have a block of dry ice and it will go and immediately sublimate, skips the liquid phase. The smoke rises off of the dry ice, right? The smoke. It's carbon dioxide is leaving the dry ice. It goes straight to a gas phase. The reverse is true at normal atmospheric pressure. It will go from the gas phase straight down to a solid block. There's no liquid CO2 at normal Earth pressures. So that's cool. Now, energy. Energy. We got to talk about the energy. Here we go. Here's a good chart. All right. Solids, liquids, gases. And then there's these two things. Did you know molecules are polite? Oh, yeah. They're super polite. So here's your question. Is 0 degrees Celsius, is that the melting point of water or the freezing point of water? Think about that. If you have something, H2O, that is exactly at 0 degrees, is it going to be frozen or melted? You've got water that's 15 degrees, 14, 13, 12, 10, 5, 4, 3, 2, 1, 0. And right at 0, does it just turn into a block of ice or does it stay 0 degree water? You've got ice that's -3, -2, -1, 0. And right at 0, does it turn into a puddle or does it stay 0 degree ice? Trick question. Because it stays a mixture. Molecules are polite because they wait. So if I have a block of ice, small block, okay, crunched up, it's all mixable, and I warm it up, the molecules go from -5 to -4. If I give it more energy, when I'm giving it energy, I'm giving it energy in the form of heat. So now they're at -4. I give it more energy. Now they're at -3. More energy. -2. More energy. -1. More energy. I give it a little energy, and some of the molecules are now at 0. Now I give it a little more energy. Some of the molecules, now everybody's at 0 degree ice, and I give it a little more energy. Some of the molecules then turn to water, and they're at 0 degree water, and I've got 0 degree ice. So we've got a mixture. If I give it more energy, the water doesn't take that and go 1, 2, 3, 4, 5 degrees while there's still 0 degree water, ice here. Everybody waits until the energy is used to turn the ice into water and it stays at 0 degrees, and then the water goes 0, 1, 2, 3, 4, 5 as you add more energy. Polite is just meaning that the energy is well mixed, the energy is distributed, and it takes energy to change phases. takes a lot of energy for water to change phases. That amount of energy that it takes to actually change from 0 degree ice to 0 degree water is called latent heat. In fact, that's the latent heat of fusion, and there's latent heat of vaporization over here if I wanted to take 100 degree water and turn it into 100 degree steam. And then you add more and it turns to hot steam. As I add energy, the temperature goes up. As I add energy, this is not really time. I don't like that as time. As I add energy, the temperature goes up. And then we get to 0 degrees. And then it stops. It stops. I'm still adding energy. I'm still adding energy. I'm still adding energy. Now it's all still same temperature, still 0 degree water. And now if I add energy, temperature goes up, temperature goes up, temperature goes up, repeat, repeat, repeat. Now it's 100 degrees. It's just on the stove. It's just about to start boiling. And I'm going to add more and more energy. And this takes a lot of energy to turn that liquid into a gas. And it's going to wait till all of it's at 100 degree gas. And then it's going to go to 103, 104, 105 degree gas and warm up. This is when things are well mixed. All right. So latent heat is the energy required to change phases. Specific heat has to do with how much energy it takes to change 1 degree. All right. Now, some weather terms. Now that we've talked about the energy in the air, let's talk about the water. Okay? So, humidity means there's water in the air. Humidity is the amount of water vapor in the air. There are lots of ways to measure it. First one's up, saturation. What does saturation mean? So, if I just take this at room temperature, cup half full of water, and I cover it up, some of those water molecules are going to start to evaporate. And they're going to add to the air molecules that are already up here. Ding, 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 ding. They're bouncing around. Maybe one of them then bounces back down and not bounces, it condenses back and rejoins the water. At the point where evaporation goes so much that you fill this up with extra water, because it wasn't just air, now you're adding water, so it's fuller. And as it's denser, it's going to start condensing some of that water back out. When you get to the point that the amount of evaporation and the amount of condensation are equal, that's saturated. All right, that is saturated. So this is the relative humidity is 100%. That means there's literally, if you tried to put more water in the air, it would just rain back out somewhere. All right. Now, warm air will hold more water than cold air. So on a cold day, the amount of water in the air is less. On a warm day, you can put more water into the air before it starts to condense back out and saturate. Warm air can hold more water vapor, which is why we talk more about humidity in summer and dry winter air. All right. Relative humidity. Relative humidity is actually kind of easy. It's the actual water vapor density divided by the saturation. In other words, how much it could hold if it was completely full. So it's how much water is in the air divided by how much water could be in the air at that temperature and pressure, at that specific temperature and pressure. So it's how much water there is divided by how much there could be at that temperature and pressure. All right. Relative humidity is one way to measure summer humidity. Here's the other one. Dew point. Here's the other one. So what is the dew point? The dew point is not a percentage. It's a temperature. The dew point is a temperature. And it's the temperature you would need to cool the air down to get to saturation. What? Well, look. If I've got water molecules evaporating and some condensing, if I cooled this down, that means there could be less blue-green water molecules in the air. So that means the number I already have is saturation. So if I cool the temperature down until I reach saturation, that is the dew point temperature. All right. And if you cool it down any further, the water that is in the air will condense out. Dew, fog, clouds. Cloud is a low fog. Dew forms on any surface that it can connect to because it can cool on that surface. So dew point is a temperature. So here's the other thing. The dew point temperature, we can use Fahrenheit for today. All right, if someone says the dew point is in the 50s, all right, so here it is, dew point's 55. What that means is that even on an 85-degree Fahrenheit day, there's only 5%, red line, 20% humidity. If the dew point was in the 65 on that same 85-degree day, that's 30% humidity. If the dew point was 75, that's 40% humidity. The higher the dew point going up on this graph, the more humidity is in the air, the more water is in the air along these diagonals. You're crossing from these. Why are they diagonal? Because you're going to condense stuff out, right? Hot air holds more water. Cold air holds less water. So 100% humidity down here, it is not that much water. Okay. This is just a different way to measure it. Some people like to hear dew points. If you hear the dew points down in the 50s, it's going to be a cool, if it's midsummer and you hear dew point in the 50s, it's going to be a not cool, breezy morning. It's not going to feel humid at all. It's going to feel light and breezy. I don't know how to express it. It's definitely not going to feel sticky. All right. What's a hygrometer? It's how you measure humidity. We're going to look at this one first. This is a wet bulb hygrometer. What do? Take two thermometers side by side. You take one, you put a wet paper towel or a wet cotton cloth around it. Soak it wet. And then you grab this handle and you go, whee, and you spin it. Why? Air is going to blow across both thermometers. The one that has the wet cloth, that air is going to evaporate, which is going to cool that thermometer. So you got two thermometers side by side, but as you blow the wind across there, one is going to get colder. The bigger the difference in temperature, the more humid the air is. Now, that's the literal, you could put a fan across it or you can spin it. That's the old way to do it. Modern hygrometers just measure humidity. Oh, no, it's going to take a minute here. Modern hygrometers are just images, just dials that read the number. It's all internal, right? They've got a circuit covered in a liquid that changes. You run electricity through it and changes the resistance as the temperature and humidity change. That's it. All right. That was a nice short one today. Guys, enjoy your day. Keep learning about that weather and atmosphere. I will talk to you